Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. What we're doing today is multivariable calculus. It's hard to say even, let alone compute. We're in chapter 2, double and triple integrals. Today we're doing double integrals over general regions, and specifically we're going to do some properties of double integrals and then a couple examples. I don't know, maybe one. We'll see how long I talk about the properties. The first two properties of double integrals basically say that if we view this double integral business as an operator or a transformation, it says that it's a linear transformation. Again, we're going to linear algebra and mixing everything together. But what's a linear transformation? Something that goes from one vector space to another vector space, finite dimensional otherwise. And we have to have that it splits sums and spits out scalars. And that's exactly what this is saying. This is the sum property, or the integral of a sum is the sum of the integrals. Sounds like I'm saying this, that you're not. You can split the sum. And if I have the scalar product of a number times a function of two variables, I can split that scalar outside the double integral and compute the volume below this guy and above this region D multiplied by a k. You can pull the scalar out. Good. These ones will help in arithmetic if you're actually computing. Remember, we're going to use these for Green's theorems and Stokes theorems, and then we're going to have tangent planes and surfaces, and then we want the flux coming off of this, and then we're going to use divergence theorem or all these kind of theorems that are going to give us double and triple integrals, and then we're going to have to use this machinery. So what some of these properties are saying is you'll probably use them without thinking, but if I have one horrible function of x and one horrible function of y or whatever, I might want to split those integrals separately, and you're allowed to, is what it's saying, and you can spit numbers out. Next properties. What these properties do are fairly useful as well. This one is just giving us bounds on, again, if we give us nasty functions which are non-elementary and we don't actually have to compute, we could actually compare sometimes and say at least it's less than this guy, and if I can compute that guy, then we can compute volumes. Remember, if these are both positive functions, then that's saying I'm trying to calculate the volume of one of the surfaces over a region D, and then the volume of a different surface over the same region D. And if this one's larger than that one, that says the volume of this one over that region D has to be larger than or equal to the volume over the other one, which is less than that guy. That's when that one is technically saying. And it helps us with, if I have a nasty function which I don't know how to do, as long as I can compare it to somebody simpler and I could compute this one, I could say this volume is at most this, and then I could get an upper bound to my volumes if I'm trying to find volumes for some reason. This one is also quite clever. What this says is if you have an arbitrary region of type 1 or type 2 and you want to know what the area of that is, you can now phrase that as a double integral. And so what I can do is say I have some region like this, and then I have x equals a, and I have x equals b, and then I have f. Oh, we didn't use f's, we used g's. Y is g2 of x, and y is g1 of x. Once I have that, I can phrase this, and what that says is they're saying that the area of my function is this iterated integral of 1, which says that this is the integral from a to b of the integral of g1 of x times g2 of x times 1 dy dx, and those are my favorite types of functions to integrate. That is going to give me a y and then a x, and then I can put everything. Yeah, this will be a whole lot simpler to compute in a lot of cases, and then it gives me the area of two-dimensional regions as well. What that's doing is computing this. That horrible symbol now is the area of that thing, so it allows me to find volumes in 3 dimensions and also two-dimensional areas. I just put 1 in there instead of computing the volume underneath there. If I make that just a 1, then I get the area of the region. Now, for the last one, why would I ever want to do this property at first, the student thinks? Because sometimes, again, remember, as many techniques as I try to give you in single variable calculus, there are non-elementary functions of 1 or 2 or 3 or any number of variables which are what we call non-elementary, and therefore I can't have a standard integral technique even though I know the antiderivative exists on those closed intervals or regions. Therefore, I might not be able to compute some of these functions. The ones we've given you can, was my point. Therefore, what we're going to do is, if our function is bounded, essentially you'll see in the example I'm about to do, I'll do it specifically and prove this result for that specific example. I'm going to basically integrate both sides over the region D. And then what's that going to say? This will be, and then I can use the scalar properties. I can move the m outside the double integral, and then it'll be m times the double integral over d of 1, which is the area of D. and then I'll get the double integral of that guy, and then here I can pull the m out, and I'll get the double integral of 1 again, and that is the area, and that's where these things are magically coming from. What? Let's do an example, and then hopefully I can shine a light on this. All right, to do this example, now what I'm going to do is, now you can hopefully see this is a hot mess, and I don't know, because of the sort of symmetry there, I have e to the sine x and the cos y, so regardless of whether I try and clever and phrase my region in terms of x or y, I don't know how to integrate e to the sine x with respect to x, and I don't know how to integrate e to the cos y with respect to y, so even if I held either constant, it seems like I'm screwed. I'm not going to be able to integrate this guy with normal techniques. Or ever, possibly. How are we going to approximate what this volume is? I can say the volume as at most this, and at least this, by using property 5. What I'm going to do here, first of all, is draw my region, which is the disk centered at 0 with radius 2. That's going to give me that guy. Then I have draw your object first, then I have the crosshairs, then we'll get him. What are we going to get? The double integral, or the volume of this guy, approximately. Then I'm going from -2 to 2, you can see, and then even if I would try to be clever and I phrase this, I would have y equals the positive square root of 4 minus x squared, and then this could be y1, and then y2 can be negative the square root of 4 minus x squared. And I can phrase this if I want to try. -2 is less than or equal to x is less than or equal to 2, and negative the square root of 4 minus x squared is less than or equal to y is less than or equal to the square root of 4 minus x squared. Yeah, that's how fast you have to talk when you do double integral approximation. Then I could phrase this as the iterated double integral using Fubini's strong version. We can write that as the integral from -2 to 2 of the integral from negative the square root of 4 minus x squared to the square root of 4 minus x squared of e to the sine x times cos y dy dx. Or I could try to rephrase it the other way, where I use that circle, and then the x, y goes from -2 to 2. Either way, I don't know how to integrate this guy, so guess what? That's out. I can't do this. Instead, what I'm going to do is say this. I could even use the actual formula property, the earlier properties, if I needed to, but in this case, I know what the area of D is. If this is my region D, I happen to know that the area of D is going to be pi r squared, which in my case is pi 2 squared. So my area is 4 pi. If I didn't know that, I could have used property 3 or whichever one it was and actually computed the double integral over that region and then done that business, and I would have got 4 pi. It would have been a hot mess, but okay. It would have been this integral, but with a 1 at least. So good luck with that. What do I now do with that? My property says this. I see that -1 is less than or equal to sine x is less than or equal to 1. And -1 is less than or equal to cos y is less than or equal to 1. And so multiplying those wouldn't change anything, so that would still say that whatever those values are, I'm going to get, their product would be between -1 and 1. If he's a positive 1 and he's a -1, I'll get a -1 at worst case scenario. If he's vice versa, I would get a positive 1. They're still stuck between there. Then what am I going to do? Now this is what people don't like doing. I can exponentiate all three and see now I've built my function. And what does that say? Aha, this guy is larger than 1 over e and less than e. Now I'm going to double integrate both sides of this, and what this says is the double integral over my region D of e to the -1 dA is less than or equal to the double integral over my region D of e to the sine x cos y dA, which is less than or equal to e, or sorry, the double integral of e. Now I can use the scalar property, property 2, to take the e out and take this out, and that tells me that using that property and using the fact that once I take that out, the integral of 1 is the area of my region, that is going to give me e to the -1 times the area of my region D is less than or equal to the double integral of e to the sine x over d cos y dA, which is less than or equal to e times area of D. And we said that that was 4 pi, so what that says is 4 pi over e is less than or equal to the double integral over d of e to the sine x cos y dA is less than or equal to 4 pi e. I had to squeeze it in there again, but this is how we specifically find the bounds for a function. but I can't integrate. That's why I would switch to doing this. What that says now is the area or the volume is at least 4 pi over E, and it's at most 4 pi times E. Who's E? 2.718281828. Next, there's one more property I almost forgot. One more. If we have a region, which I don't want to get into points of, I kind of really do want to get into point set topology, but not in this video. In one of our other videos we'll do. I don't want to get into too much point set topology, but if we have a well-behaved region D where basically this, if I can split it and they don't share points except possibly on their boundary, or if they're completely separated, and I can view a region D as the union of two other sets, like this, then we can say that those volumes over the surface, if we're interpreting it that way, the volume is additive. If I had now my surface and my volume was here, it would be the volume of this one plus the volume of that one. That one seems obvious. But even here, if I had my surface out here and I take the volume of that, cutting that into two pieces, that plane or whatever, that won't have any volume involved in it, so we can cut it up into as many pieces as we want. You can do a D3 if you want, and then what are you doing? Stop that. Well, everyone wants their own country, so there, now you got a map. And if you want to do that, then still we can do this. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch more. Next time what we're going to do is double integrals in polar coordinates. You didn't like this in rectilinear Cartesian coordinates? Oh, wait till you see it in polar coordinates. See you next time.